All right, so this is a more colorful picture of that, obviously. So you got this conducting rod, that's just a metal piece, and you're just driving it across the magnetic field. By using the right-hand rule, number one, positive charges will experience a force in the upward direction, the negative charges will experience a force in the downward direction. Positive charges will accumulate at the top, negative charges will accumulate at the bottom. There's going to be an electric field in this direction, and there's a separation distance, so which means that there's going to be a voltage or potential difference. What that means is it turns into a battery because of its motion across the magnetic field. All right, so here's a better representation of it. In the math portion of the test, there's going to be a problem related to this, the multiple choice section of the test. This is a straightforward problem. Notice that you got the magnetic field going into the page in this region, and you got your metal piece, it's a metal, a rod, all right? As soon as you start to drag it in this direction, obviously there's going to be a voltage or potential difference, so this becomes a battery. And then you could just put it on some kind of a current. You got these wires, I was going to say current loop, maybe that's a good way of saying it. It's called a conducting rail, so which means that you're moving this metal piece in this direction. And because it acts like a battery, it's just that it's going to drive the charges in this direction. So positive charges are moving in this direction. So you can turn it into a current loop. And obviously you can generate light out. All right, also remember you're increasing, there's a change in flux within this region. So another explanation is the current is going to move in a direction that's going to oppose the change in flux. There's a much more rigorous mathematical treatment of this concept that I'm not going to get into, not at this level. When you guys take it at a higher level, though, you will see that derivation. I want you guys to kind of get the concepts and understand the formula at this level.
5, 4, 3, 2, 1. And we have liftoff of the Space Shuttle Columbia, continuing space research.
Magnetic field generating enough energy to power a space station.
All right, so this is the wire. I don't know, was it like 2 miles long or something? They were dragging it across the Earth's magnetic field, and they were able to generate a tremendous amount of current. Okay. Eventually, it got so hot that obviously just it got burned down.
We see the tension go way down, but the tether's still going down fine. Very slight lateral oscillation.
Let's go through the math real fast. Let's do one more review. I'm gonna keep reviewing this stuff. So Faraday's law. All right, so this is something that Faraday came up with about 1830. The way he was looking at it, though, if you just change the strength of the magnetic field within a current loop, it would generate current, that's it. So you're varying the strength of the magnetic field inside the area of the loop, so it's gonna induce current. All right, so you're varying the strength of the magnetic field inside this loop, it's gonna induce current. All right, so that's one way of looking at it. There's a second way of looking at it. If you vary the exposed surface area to the magnetic field by spinning it. All right, so here's your area, and then you're spinning it inside a constant magnetic field. Notice that the magnetic field is constant, so there's no change in the magnetic field value. All right, so you got a constant magnetic field, you're spinning the loop. So the area which is exposed to the magnetic field is actually changing. So if you vary the area exposed to the magnetic field, that in turn is going to induce current. All right, so I'm going to just add to the notations a little bit. So these are vectors. Let's use the vector notation, or else it doesn't make a lot of sense. All right, so varying the strength of the magnetic field inside the area of a loop is going to induce current, so you end up getting current flowing in this direction. Or if you spin the loop inside a constant magnetic field, the area exposed to the magnetic field is going to vary, so that's also going to induce current. All right, so combining these two concepts into a single concept of flux. In this case, flux is the amount of magnetism intercepted by the area of the loop. So this is the area of the loop, just doing the intercepting. You can induce current, that's it. So varying flux is going to induce current. Time variation of flux is going to induce current. All right, so here's the vector notation of the flux. Here's the scalar representation of the same thing. So any variation of flux induces current. So speaking of varying flux, you can vary the strength of the magnetic field, or the area, or the angle between the magnetic field and the area vector. All right, so what it does is varying flux is going to induce voltage, and voltage in turn is what drives current. All right, then we will have a negative sign up front. Negative sign is going to come from the Lenz's law. Okay, simply put, the induced current is going to flow in a direction that's going to try to oppose any change in flux. All right, so you have a negative sign indicating that the current is going to flow in a direction that's going to oppose change in flux. Okay, so that's your Lenz's law. Okay, I think this is the last thing we did there. motional EMF, electromotive force. All right, so you can generate an electromotive force, which means that you can generate a voltage difference inside metal, in this case a metallic rod, if you just drive it across a magnetic field. All right, so if you move it across a magnetic field, free charges inside, the positive charges will experience a force in the upward direction. They will accumulate on top. The negative charges will experience a force in the opposite direction. So there's going to be a separation between the charges. All right, so one end is going to be positive charged, the other end is going to be negatively charged, and there's a separation distance. So there's an electric field from positive to charged region towards the negatively charged region. And electric field strength times the separation distance is going to give you the potential difference. All right, so in essence, this rod is going to act like a battery. All right, so faster this thing is moving, larger the electromotive force is going to be. Larger the distance between the ends. Once again, the larger the electromotive force is going to be, the stronger the magnetic field is, larger the electromotive force is going to be. All right, that's it. How do you generate current? Current is generated just about the same way, ever since 1880s. The only thing you have to do is just get a loop of wire and just spin it inside a constant magnetic field. All right, so in case there's a test question, obviously there will be plenty of questions on this one, conceptual questions. All right, so change in flux is what generates the electromotive force. And the way we change flux is we keep the magnetic field constant. Obviously, the area of the loop is also going to be constant. The only thing we vary is the angle. All right, so this tells you how fast the angle is varied in terms of its angular frequency. All right, you end up getting a sine wave, which means that the electromotive force is going to keep changing direction, goes up and down, which means that the electromotive force going the direction of the wire. What it does, it just keeps changing direction 60 times per second. And the term that you're looking at up here is going to give you the maximum value of the electromotive force. So the maximum value of the electromotive force is going to depend on how fast you're spinning the loop. All right, so that's the angular frequency of the loop that you're looking at. Okay, so here's a question for you. It's an open-ended question. So if you kind of know the answer, just jump at it. Why do we use 60 hertz for this one? All right, so in the United States, the current is 60 hertz, which means that the current changes direction, or the voltage changes direction 60 times per second. Why not make it like 120? Why not make it 500? What's the advantage of it? More often you change the direction, larger the electromotive force is going to be, bigger the current is, guys. So why not spin the shit out of this thing? Just go nuts.
Does it wear out too fast? The bearings couldn't handle it on the generators. I don't know.
Or you may go flying.
Let's force to stop it, right? Take a lot of force to change it and go in the other direction. So you probably want it relatively low.
Okay. All right. I'm gonna make this. I'm asking this question because I have an answer, but I'm not sure if it's the right answer. Okay. This is a bit of a research question. I wonder why they decided to say, why not make it 70 hertz or 50 hertz?
You're raising at 50 hertz.
Because they just decided. Is it just because they just decided 60 hertz and didn't want to change it? Like, there's really no reason why they haven't. They just kind of decided 6 hertz in the beginning and then didn't want to change it.
Okay, Lucas, I'm going to give you 5 points. Every single person who says something, I'm going to give you 5 points. Okay, so change of flux is going to induce an electromotive force, right? All right, so the change of flux induces an electromotive force. All right, guys, take a look at this region. Within this region, I'm going to change the flux. And then when you change the flux, what happens? If you were to place a wire here, within the wire, you're going to have a current, right? Okay, so change of flux. I'm going to change the flux. All right, change the magnetic flux is going to induce current. The reason why that happens is because, all right, let's pretend that you got a number of turns here. It's because it causes an electromotive force. All right, so that's the way it is done. Okay, so what does the electromotive force do? You got the electromotive force, which is going to drive the current within the circuit. All right, so I'm going to change the flux within this region. I'm going to keep the area constant, vary the strength of the magnetic field, and it's going to cause a current. All right, so that's the meaning of the Faraday's law. Okay, so now we will make it a little bit more abstract. the abstraction happens like this. Whenever we are talking about the magnetic variation of the magnetic field causing an electromotive force, so you're varying the strength of the magnetic field within this area. In doing so, you vary the flux. In turn, you end up having an electromotive force that drives the current. Okay, guys, the electromotive force by definition is the same as voltage. And voltage is the amount of energy stored within the electric field of two opposite charge regions, which are separated by a distance r that we were looking at. Okay, so we will make this a little bit more abstract. We started off about a month ago. Okay, this is, I think, a concept that we were discussing. We were looking at two separately charged regions. And within these two separately charged regions, you have the electric field, and then you get the separation distance. And the voltage potential that you're looking at represents the amount of energy that's going to be stored within the electric field between two opposite charged regions. Okay, so what's driving the charges in this direction is a circulating electric field. That's what it means. All right, so within this region, we're setting up a circulating electric field. All right, so what that means is when you vary the strength of the electric field within this region, you end up creating a circulating electric field within that region. All right, so what's happening is it causes a circulating electric field. And then if you place a wire within that region, what's happening inside the wire, it causes a circulating electric field along this direction. And obviously you have charges. I'm just going to put a negative charge here. And there's an electric field acting on it, so it's going to experience a force on it. So it's just going to move. It's going to accelerate in that direction. Okay, so that's what it means. So we will add on to this definition. So I'm just going to add on to this definition. So even if there is no wire within this region, what's happening is you end up creating a circulating electric field. So the electric field is circulating within this direction. All right, so what's happening is we have a circulating electric field within this region. All right. This ds is like the separation distance r over here. And all of a sudden we were able to make a leap. So when you change the flux within a certain region, all right, and within the region of this area, all right, let me just make this clear. So this is the area that we're looking at. All right, so this is the area of the region. And then we're changing the flux within this region. So here's the area. This is the same as this. And then you're just changing the flux within that region. All right, so you're changing the strength of the magnetic field, it changes the flux, it causes an electromotive force. The electromotive force sets up a circulating electric field. And ds is the same as the separation distance here. All right, so it sets up a circulating electric field through the circumference of this region. Okay, and all of a sudden we came up with something really interesting. So when you change the flux within a certain region, you're causing a circulating electric field within that region. And if you place a wire in there, obviously the charge will experience a force in the direction of the circulating electric field. All right, all of a sudden this becomes a little bit more abstract. All right, so that's the meaning of this slide deck we are looking at. Notice that you're reducing the strength of the magnetic field within that region, which means that you're changing the flux within that region. And when you change the flux within that region, it's causing a circulating electric field. So you can reduce the strength of the magnetic field. Well, now, at this point, there's no change in magnetic field. All right, and then now let's increase the strength of the magnetic field. All right, if you go in the opposite direction, when you start to increase the strength of the magnetic field, this time the electric field is going to move in the opposite direction. All right, let's take a look at a derivation. Before we take a look at a derivation, take a look at this one. All right, more than likely your extra credit test question is going to be related to this. Show work type of extra credit, obviously. This is simple enough derivation. Once you get the hang of it, straightforward. All right, so we got a copper ring within this region. And then take a look at the yellow region. Within that yellow region, the magnetic field is pointing into the page. And then we will vary the strength of the magnetic field within that region. And then by varying the strength of the magnetic field within that region, you can get a circulating electric field within that region. So if you increase the strength of the magnetic field, the electric field is going to circle one way. And if you decrease the strength of the magnetic field, the electric field is going to actually reverse direction circle the other way. That's what it means. All right, so electric field lines within that region, within the region, inside the region within which you're changing the strength of the magnetic field. And then the electric field lines will also exist outside of that region as well. All right, so this is problem number 6. Instead of doing problem number 6 numerically, we will do it conceptually. Not conceptually,